So the first thing we want to talk about is what does a biased neuron do? So we have this thing that I've been talking about as a biased neuron, which puts out a 1. And it goes into all of the other neurons above, even the hidden and the output. So let's just calculate what are the neurons. Now let's calculate the net input and then the output for that neuron. So what we get for the net input is the sum well, let's call that neuron model. Let's give it a name. Right, so it's the sum of the weighted inputs of all the neurons feeding into it. And notice I went from 0 up to the total number, and we know that if there's connections that aren't there, especially the ones coming backward, then those weights are just 0. And then the x, the output, is f of that thing. And we talked about how if all of the inputs are 0 here, then all of the x's coming out of the input layer are going to be 0, and you'll always get a 0 out. And you guys saw that with the homework problem, with the not OR gate, right? Where you get 0, 0 in and 1 out. So how do we fix that? If all of the inputs are 0, you're going to get a 0. Well, we can use that bias neuron. That's part of the sum. So let's separate out that one. And the output of the bias neuron is always 1, so we got a 1 there, plus all of the other stuff. Like that. And so what that means is that this bias weight can shift the net input so that you can get a non-zero output even if all of these x's are 0. Because the bias always puts out a 1. So what that does is if you have this activation function f that looks like that, if you add a shift to it, then that shifts this, say, over to here, where now we're talking about a function of this thing here. You're just shifting, you're adding a bias to it, so it shifts this way or that way. And that's why you can get, even for a 0 net input, you can get a non-zero out. So you can think of it as shifting the f, or just looking at it obviously. If you have this here, then you can add that to a 0 coming in, and you can get an output out. So that's why we do bias neurons. It shifts the f function and expands the range of values that you can get out of the f function. In other words, for a 0 input, you can get an output. And then if you train this thing, then you can use backprop to train that weight, which means that it will learn what activation functions it needs to shift and by how much. So it becomes part of the learning is how much the bias affects it. So when you're running NeuroWorks, there's that box that you check for the bias. And you will almost always have that checked. And so with NeuroWorks, you'll always create a bias neuron. All right, so that's the story about bias neurons. And then the other thing that NeuralWorks does is it scales the input and the output data. And there's two good reasons for both of those. So that's what I want to show you next. You remember in the video I showed you there's something called the min-max table? And we unchecked that because it turns out that the iris data is already scaled. The data itself is scaled. But most problems that you'll deal with, it won't be, and so NeuralWorks will auto-scale it for you. But here's why we would want it to do that. So the first thing is that you scale output data. And here's a real quick example that shows you why you do this. So let's say we have a robot arm that rotates. So it's a real simple, just a single link robot arm, and this thing can rotate about that point. And so, and we'll actually work an example like this. Measure this angle theta. We want to apply a torque to this and use a neural net where the output of the neural net is theta. Model this artificial neural net. Output, the only output is theta. And so we're going to have a neural net with some inputs that will probably be like the torque and the current value of theta. And we want to predict theta at, say, the next time step. So we'll send in where theta is now, where theta was 1 second ago, and then we'll send in the torque. That makes sense. We ought to be able to do this, right? You know where the arm is. You know where it was a little bit ago, so you know how fast it's rotating. Then you know how much force you're putting on it, how much moment. So you got to be able to calculate where it ends up at the next time step. There's an issue with this, though, because theta, let's say we do this in degrees, theta is going to go from 0 to 360. And this neuron is going to have an activation function. So let's say we do the activation for this, which is the hyperbolic tangent, because it'll allow it to go positive and negative. That's good, right? Maybe we'll have positive angles and negative angles. 0 to 360, or maybe plus 180 to minus 180. So we do this, but this function maxes out at plus and minus 1. So we're saying, hey, let's use this neuron to output values of theta between minus 180 and plus 180. Let's just choose that example. Is that neuron going to be able to do that? You can put out plus 1 is the biggest and the smallest is the minus 1. So all we have to do is scale the data to fit the output activation function. And so for this, you typically scale the data. Maybe, I mean, it'd be really easy here, say divide by 180, right? And if you do that, then you get, say, we'll call theta hat is the actual value divided by 180. And so theta hat is what we're going to ask the network to predict. And it's going to go from minus 1 to plus 1. And so the activation function can do this. So we scale the data. Now, if you look at this, this doesn't ever actually reach all the way to 1. This doesn't reach negative 1. So maybe you'd want to divide by 190 to squish that scale down a little bit. And in fact, that's what NeuralWorks does, is it does the min-max table for all of your output data, whatever you're saying, here's my outputs. It finds the minimum and the maximum, and it scales based on those. Because that's what we did here, right? We said, okay, here's the minimum, here's the maximum, so let's scale by dividing by that. It's possible that we would say that this range only goes over there. So we'd still divide by 180 maybe, but then that squishes it down to maybe only using this range of the activation function. So in fact, what we'd like to do is shift it so that the average is in the middle and then scale. And NeuralWorks does that for you. And all that's stored in the min-max table. It finds the minimum and the maximum and shifts it to get the range covering the whole activation, and then divides to get it to fit. So that's nice, it's done for you. And that's why you scale the output data. And it's even nicer in NeuralWorks because it does it for you, and you can feed it the data like this. It scales the output values to, say, plus and minus 0.9, does the calculations, and then actually scales it back for you. So the data that it's going to give you back is back in the unscaled variable. So it's all done inside NeuralWorks, very transparent. It's nice. Okay, so you scale the input data. The output data. NeuralWorks also does the same thing for the input data, but for a different reason. So we do the exact same thing. It looks at the maximums and minimums of each of the inputs and scales based on that. Same deal. It shifts, it finds the average, and that's actually not the average, it's the mean. Median, right? That's the middle value. It shifts and then scales based on that. It does exactly the same thing on the input data, but for a different reason, and here's why. So let's draw our network again. Here's our input layer. Let's say there's 10 of these, so this is input 1, 2, number 10. And then let's isolate one neuron in the hidden layer. Right here, so this neuron number 5. Okay.
Could you lower the monitors?
Oh, yeah. Let me get the table all the way down as well. Is that far enough, or do I need to tilt them a little?
I think it's good.
Usually I tell the people, usually there's people sitting up here. I know we're all physically distancing. Usually I tell them that their job is to remind me to do that, so now it's your job. Okay. Or your job, because you probably can't see very well either. All right, so this neuron takes in inputs. Well, we can even put the bias in here. Takes in all these inputs coming in. Multiplied by the weights. By 0, by 1, by 10, right? So let's write that down. What's going into that neuron? Here we can be really specific. J goes from 0 to 10. Right? And these X's are just the input values coming out. So let's say, just for the sake of argument, that all of the weights are 0.1, and all of the x's, which are equal to the inputs, have values of like 10 to 100, or maybe measures or something. So if we start adding up this net input, we're going to get a number like 10 times 0.1, so we're going to get like 1. Maybe there's a 50 times 0.1, so we're going to get a 5. And then 100 times 1.1 is going to be 10. And you keep getting these numbers, so I'll just pick some numbers in that range. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the net input. Multiply the weights times the input values. What does that add up to? You're going to find out I'm not real good at adding in my head, so let's give it a shot. 16, 23, 31, right? 37, 42, 52, 62. I get that right? Amazing.
Wouldn't there be a 0.1 for the bias neuron?
Oh, I forgot it too. Thank you. Told you I was bad at adding in my head. I even forgot to add it. When I was like in middle school, I built an abacus. You know what that is, right? The beads, and I got really good at it. You can add fast in it. I challenged my neighbor to a race at adding numbers. So I had his brother say random numbers, and we'd add them together, and he'd beat me. Turned out he was really good at adding numbers in his head. I mean, these were numbers like 1051 and things like that. And he turns out he went on to pharmacy school. He was a smart guy. Random story there. So what's our net input? 62.1, right? Now let's apply the activation function to that. Where is that? Let's say this is a tan-H. So our neuron here is a sigmoid tan-H. Let's draw our tan-H. 62.1 is going to be way out here. We're going to get a 1 out, which is okay. A 1 coming out is fine. Except we're going to say, okay, backprop, change the weight of this connection to give me a better output. So I look at that and I change the weight from 0.1 to 0.11, and that's only going to change one of these a little bit, right? Actually, maybe that'll go a little better, right? So that moves the point where we're at to 62.2. And I still get a 1 out. This neuron is said to be saturated because even fairly significant changes in the weights in the layers doesn't change the output. It's always firing. It's saturated. It's kind of overstimulated. On top of that, and this is illustrated by backprop. Remember, backprop has F prime in the formula. The learning rule, when we calculate the error deltas, we get the error deltas from the neurons above times F prime. What's F prime? Right here. It's the slope, right? So what's the slope of that thing? Yeah, so the slope of the saturated neuron is 0. So all of the error deltas in all these neurons are saturated are going to be 0, and no training happens. And that's just reflective of what we talked through. If this is flat like this, changing the weight, changing the net input doesn't change the output, so the backprop is saying, I don't know what to do, because no matter what I do to change the weights, nothing changes. So how can we fix this? We scale these inputs. And we choose small weights initially. Usually small isn't like 0.1. You'll choose a weight like maybe 0.01 or 0.05. And then you scale all these to be less than 1 so that the max and min is less than 1. And so when you take less than 1 and you add them up and multiply by the small weight, you're still going to be in this unsaturated region of your activation. So that's why we do scaling of the inputs as well. Again, all done by the min-max table. Now I want to show you a couple papers that I scanned in. All right, you guys can see that, right? Yeah, and it should be shared on Zoom. Okay, this paper talks about how do you prepare the data for a neural net. And you'll see in this paper or the next one that it will say the scaling. So that's a key feature, is you have to scale the data. But another key feature that we talked about briefly when we talked about French translation is you got inputs that are letters, and you have to figure out, well, how do you encode the data to be numbers in the neural net? This should be posted on Blackboard, but I wanted to point out a few things. It talks about how maybe you're talking about predicting whether food is good or bad, and the temperature of the food is important in predicting that. So do you put in 101.5 degrees F? Or do you put in frozen, chilled, room temperature, or hot? In other words, do you encode it as like a category variable, or do you put in an actual number? So one way would be obviously 101.5 degrees F, is that maybe that's good for your quick trip hot dog, right? It should be a little hotter than that. Sorry, we eat hot dogs from Quick Trip quite a bit. They're cheap and they're pretty good. Or you could put in an input that has a 0 or a 1 representing which category it is. Is it frozen? Is it cold? Is it hot? Is it burning? So you have to decide what's the best way. And often, if you're trying to predict some kind of category information, you don't put in the actual number, you'll put in a category as an input. Here's another thing it talks about. It says a common mistake is using continuous valued inputs to represent unique concepts. So maybe you're trying to predict when people will buy oranges. And for a grocery store, do you put in the month of the year, like January? Do people buy a lot of oranges in January, or do they buy more in June? But if you might be tempted to just put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for the month. And that's not always good, because is December as a 12 times more important than January? Probably not. So again, you might create categories. You'd have an input neuron that represents January, another one that represents February, and so on. So it talks through that. Pull this up and read through it. Sometimes changes are more important than the actual value. Like today, you guys own stock? Are you invested in a retirement account yet? Or care whether, I think when I was your age, my dad has some stock. I used to play a stock market game. The Dow Jones Industrial Average closed today at 31,613, which is kind of amazing because we're in the middle of a pandemic. It's at a record high. So if you're trying to predict the stock market tomorrow, maybe you're tempted to put in 31,613.02, plus other variables like the foreign exchange rate and everything else, right? And who the president is, for example. But maybe you don't want to put in actual values, you want to put in changes. You don't try to predict 31,614 tomorrow, you predict that delta increment of 1. So sometimes it's better to put changes in values rather than the actual value of the day. So they talk about this here. And they go through a nice example of whether you're interested in buying a condo or not. They collect your name, address, sex, age, marital status, years of school, and they're trying to predict how likely you are to buy a condo so that they know whether to target you with a robocall, which you then hang up on and don't listen to. Literally in the last year, I have gotten 100 calls telling me that it's my last chance to buy an extended warranty for my car. If I don't act today, yeah, I'm sure you've gotten them as well, right? So they collect this data and then they talk through, well, how do you represent this? Like the zip code is not input as like 67230, which is my input, but maybe just the last 3 digits because we're just using Wichita and only the last 3 digits in the zip code change in the data in Wichita. Sex they'll encode not as an M because you can't put in the letter M. You have a 1 or a 0 in 2 different categories for male or female. Age, again, is a scaled variable. Your years of schooling would go in as a number. Number of dependents is a number. Your income is a number. But notice that there's a choice as to do you do a category variable or do you do a number. It wouldn't make sense to say, well, if you're a male, you put in a 1, and if you're a female, you put in a 2, unless somehow that bias is actually correlated to what you're trying to predict. So here's what they came up with to input to the network. Notice that there's a separate input for each zip code, 3-digit prefix. And so if they're in this zip code, a 1 goes in here and a 0 goes everywhere else. And then here's the sex that's encoded as a 0 and a 1, but then these are actually put in as numeric values except for your marital status as single or married as a category variable. And all they're trying to do is predict what's your likelihood to buy a timeshare condo. Here's another example. They're trying to predict the Dow average for the next month, and notice they're predicting the change. And they put in all kinds of data here, which month it is, and what's the unemployment rate and everything else. And those are related to some of those other examples I showed you. They talk about trying to find the border patterns, which means the edges of the data. In other words, if you're in the middle, you're most likely to buy a condo, but you want some of those people that are kind of the border patterns that might or might not buy a condo so that you can differentiate better. So I'll let you read the rest of this. This is another paper I've uploaded, Preparing the Right Data Diet. Key features here, we've talked about a lot of these, scale the data. That's obvious, I've showed you why. Make sure you gather enough data. In fact, the more data, the better, typically. There's a few other things I want to point out here. Maybe. Oh, this is in the handout that I gave you for NeuralWorks. It helps answer the question of, well, how many hidden neurons do you use? And they give you some rules of thumb here. This is a good rule of thumb. H is the number of hidden neurons. Cases is the number of training pairs you have. And M and N are the number of outputs and inputs. Doesn't always work, but it's a good place to start. Again, it's a rule of thumb. And then out of a different textbook, is, where's the rule of thumb here? Here we go. So there's another textbook that has a rule of thumb. For pattern classification, you can use m times n to the 1/2. If m and n are large, use this. For function approximation, which tends to be what we do in controls, because we're modeling functions, then there's a different formula here that you can use. See the stuff I've boxed in green, they're formula for initial guesses only. Typically what you'll do is you take a guess, and then you'll vary the number of input neurons and see does it help or hurt. Add more, take away some, and see whether you get better results or worse results. And I'll talk more about that when we get some assignments going. And in fact, you have a new assignment to run NeuroWorks, and it's really just playing around with different numbers of hidden neurons for the iris problem. And then the top problem will take you a little bit of time. It's a derivation just like I did on the board for the back prop. I want you to just go through that so that you write it out and you see it happen. It's not a lengthy derivation, and it's real similar to what I did on the board last time. Okay, let's stop this one. Then I have a fun article. The title of this paper is called "No, We Need a Neural Net." Let me share that. There we go, got rid of the blue. Oh, it's kind of random. So this is a kind of interesting article written a while back about a company that wanted an expert in neural nets to fix a problem and how it went. So this guy, MA, it's just his initials to protect the innocent. You did an undergraduate specialty in artificial intelligence, master's thesis in genetic algorithms, and doctoral dissertation in evolutionary programs, all AI learning methods. The company, which will remain nameless, wanted to hire him, a small programming firm that maintains software used by the Bureau of Wastewater Management, water management. They said, we want you to create a neural net to manage this database that we have of the water management. He looked at it and said, neural networks are not the right tool for this job. And in fact, the major takeaway I want you to have beyond how do you do neural nets in this class is what is a good neural net application and what is not. So he said, what you're asking me to do is a waste of time. There are better ways to do this with simple statistical methods and calculation. I like this part. Had they not offered him such a generous salary, he might have recognized that that was a problem. But anyway, they offered him money. So I spent a few weeks analyzing the system, figured out how to parse the data and all this and use a neural net. And after all that, spending some money of their money, he said, this is still a very bad idea. Management disagreed. They said, neural nets are the way of the future. We want a neural net. He said, fine. He worked for a year on this, collected money, collected a salary, created a system. The system required a server cluster to run the analysis using the neural net and all of the data. Actually, it was much worse than what they were doing before. Finally, he's tried one more time. He said, let's drop the neural net and use just straight statistical methods. You with me so far? So 3 years later, the programming firm was bought out. New management team comes in. The chief technology officer said, what's this giant thing that we're supporting to do our wastewater management? Contacted the guy who created it and said, I told them this was a bad idea, but we did it anyway. So the CTO said, well, let's fix this. And so they took away the neural net, they brought in and paid the guy again to develop the traditional statistical method, and all was good. So the chief technology officer said, well, we got to do something with this. We spent money with it. So he pre-programmed it to work from a data set of phrases instead of the wastewater data. And it would output actual sentences. So essentially he just put in an input and it would randomly create sentences that made sense. And here's one of the things it created. The pig go is to the fountain, the pig put foot, grunt, foot in what? Ketchup. The dove fly is in the sky. The dove dropped something on the pig disgusting, the pig rattle with dove, the dove angry, the pig leave. The dove produces chicken wing with wing bark, no quack. So that's what they got out of this giant neural net that processed wastewater. Changed it to processing phrases and words. All right, so that's a fun but illustrative reminder that not everything that seems like it would be fun to do with a neural net is actually a good thing to do. So again, part of what my job is to help you understand how to do neural nets. And then when you get out on the job, you know, well, hey, this looks like a good application for a neural net. Let's try it. Go to your boss. It works. It impresses him and everything looks good. But you'll also know, well, this isn't really, there's a better method for this other than neural nets. So this is the end of our introduction to neural nets. So this is the basics. It's by no means exhaustive. There's all kinds of stuff way beyond this. There are pattern recognition deep learning networks that are called convolution neural nets, where the activation functions are convolution functions. They get convolved with the input pattern. And so it does pattern matching between the input, like a speech pattern that you do speech recognition or image recognition. We'll get into some other neural nets later on called self-organizing maps. These networks are feed-forward supervised learning. Have I used that word before? We're talking about how it's feed-forward. This is about ready to go. It's also supervised learning. Because there is essentially a teacher. You know, where's the teacher? Well, backprop requires the correct answers with target values. Right, so essentially that list, the training pairs data, the inputs, and the correct outputs are the teacher. It's examples. It learns from example rather than be instructed, but it's still supervised. You're giving it the correct answers and it can correct itself over and over again to get the right answers. There's another form of learning that does not have correct answers, and that's what we'll do later on in the semester. It's another powerful tool. It's called self-organizing maps. You would feed it, let's say, the iris data, and you wouldn't tell it what categories there were, and yet it will automatically sort the data, the petal and sepal values into categories, and you'll see the actual 3 different types of species that are encoded in the data. So it's pretty cool, and it works well for certain applications. So that's the end of neural nets, even though there's a lot more. There are some good machine learning classes taught in computer science and electrical and computer science here at WSU, as well as elsewhere. So if you really get excited about AI and machine learning, I encourage you to take one of those classes down the road. Now let me see if I do have NeuralWorks on here. If I do, show you what we missed the other day. Sorry, I'm gonna have to poke around here. It's not installed in the normal way, so I can't just look for it here. Try one more place. Sure, give it a minute to copy. I'm going to just copy it onto the desktop here. Hopefully it will launch it run okay. Okay, I got it launched. Let me share my screen so you guys can see it. All right, so here's NeuroWorks, and we're going to create the network. We'll do the same thing I did in the demo. We'll do the iris problem. So that's 4 inputs. Let's say 4 hidden neurons. You can see this right now. 3 outputs. I can do connect prior. I'm going to do the next payload by 4 inputs. Well, I was wrong. There's no checkbox for the bias. It just automatically goes in. There, an older version used to have that. We're going to do the delta rule, sigmoid. There's the training data, the testing data. Set epoch from file. Say OK. Unless there's something we want to look at. I'm going to run this. Now, before I do that, I want to check the current directory and make sure I'm going to be able to find what we generate here. So if we're good, we're on the C drive on the desktop. We'll run this, learn for 50,000. Learns. We're going to test it. Testing is what generates the .in and R file, which are the results file, and that's what I want to show you. So the error is worse, like I said, because there's some measurement error and it misclassified, and that's part of what I was showing you. So here we are in the installation directory for NeuroWorks. want to find the iris data set first. So this is what the training data is going to look like. Let me share this screen here. You can share the points down here. Share screen. All right, so this is where I went into not Internet Explorer, File Explorer, found iris underscore train. This is the training data set. That looks like this. And you guys didn't see this, right, in the video? Yeah, so this is the structure of the data set. Here are the input values, the measurements, and then here's the category. So this one is classified as the first category. It's a setosa. That's what the 1 here means. And the ampersand that I was talking about is just a continuation. So if you put the ampersand, then this is the entire training pair, inputs and outputs. You can actually just do this and put it all in one line. That's just as good. Often I like to do this as opposed to put the ampersand in, but it kind of emphasizes what's inputs and what else, but what's outputs if you do separate lines. The exclamation mark is comments. And if you do this @ symbol, it will create these labels for the inputs and the outputs on your network. That's all that's doing. So that's the input data set. And when you create data sets for NeuralWorks, this is the format you'll use. It's an ASCII.NNA file. So if you put NNA, you'll just save it as an ASCII data file type, and then open it in Notepad, and you can save it as an NNA. No, don't change. And then when we did the testing, on the testing data set, it creates this data file called iris_TES, same name as the .NNA file, but it puts a .NNR. Follow that? So we tested on that thing. And when we do that, it generates a network. So the target was a 1, and the network gave us a 0.993038. Pretty good, right? We wanted a 0, and we got a 017. And here we actually got 0. And this works well. The second training pair is supposed to categorize in the middle category. It does a really good job on that as well. Keep looking down through here. Notice the structure is diagonal here. So we can glance through and see the diagonal structure there. And here. And here. So those are all looking really good. Down through here. And if we go far enough down, help me find that there's a couple cases where that's not true. Here we go. This is one of them. Look at this set here. Did we get that right or wrong? We wanted a 010, and we got a 0.2 where there should have been a 1, and a 0.8 where there should have been a 0. So that one is misclassified. It's saying it's the third category, and it's only the second category. I think there's another one. Does anybody see it?
Right underneath.
One right under it? Oh, yeah, it's giving us a 0.7 in the middle, and it should be a 0. So it's misclassifying that one. So the results file is important because we will run neural nets, and then often we'll post-process the results and plot. And so that's where you get that. As far as generating these data sets, there's 2 different ways. Well, there's several different ways you can do it. Most students will use Excel and then dump it out as an ASCII file. So you can do the calculation in Excel. Some students will use MATLAB because you just write to a text file and you're done. And some of the applications require you doing loops, like to generate data like that rotary robot arm. You can do that in Excel, right? You just do cells down that create values. It's whatever you like to do. Occasionally, a while back when computer science students used to learn C all the time, every once in a while somebody would program in C. AE students used to learn Fortran, so sometimes students would program in Fortran to do this. It's your choice. You can use BASIC or Python or anything you want. Most languages I could help you with. If you get off into something really weird, I probably wouldn't do that. Just out of curiosity, I'll ask this again when we do the first assignment. What are you most likely to be comfortable with as far as generating data sets? How many people in MATLAB? MATLAB? Excel? The rest of you guys? Yeah. Either one works. I really don't see much difference between the two. All right, let's call it good for today. Yeah, the homework assignment. As part of your first assignment to go find neuron, so you okay, I couldn't do that, and I couldn't do it. You were able to find it, so it is there, and it should run. The caveat is that if you want to save a network, you'll want to copy it to a jump drive. You can save it locally on the machine. Like typically, you'll just change the current directory to your jump drive, and it's all safe there. Okay. All right. See you next week. Monday. It's supposed to be like 55 degrees. Everybody shut up and shorts and t-shirts. Yeah, just shut this down.